Okay, so today we're going to talk about recursion. One of the cool things about recursion is you find it pretty much throughout life. The picture on the left is from MC Escher, and the picture on the right is the Sierpinski gasket. Both of those display great examples of the principles of recursion. Sorry, the Escher is not so clear in the PDF version of this, but you can look up some of Escher's work online. He uses a lot of really cool recursive structures. And, definitely an artist worth looking at. So let's get into a definition for recursion. And the humorous definition is C, recursion. The dad jokes are going to come fast and heavy during this lecture, and I apologize in advance for that, but there they are. So a real definition, and this is from our Malik textbook, is solving a problem by reducing it to smaller versions of itself. And so recursion provides a really powerful way to solve certain problems which would be very complicated otherwise, and sometimes those iterative solutions, they do exist, but they're not as obvious as the recursive version. In C++, it's a function definition that contains a call to itself, and that's what makes it a recursive function. So a typical approach to solving a real-world problem is to break a task down into a series of smaller tasks, and this is known as stepwise refinement, work breakdown structure, functional decomposition. It has a lot of names, so it's a really important concept throughout a lot of different fields in academia. You can think about this planning a party or planning a wedding post-COVID. You'd like to have a huge wedding. How do you do that? Well, you need to determine who to invite, determine where the venue is at, which dates are available for the venue, what's going to be served on the menu. And then you take each one of those tasks and break it down a bit further. Probably need an efficient as well. You break each one of them down further until they become an atomic task that you can hand off to somebody and get that accomplished and check it off your list. And so, that appears throughout the business world, appears in academia, computer science. It's not just unique to us. But whenever one task is a smaller version of the original task, you can solve the original task using a recursive function. So I'll give you an example. How do you find the lion in the zoo? Well, the solution is you look in the first cage. If the lion is not there, look in the rest of the zoo. So you look in the first cage, not there. Okay, the rest of the zoo is separated over here. I'm going to look in the first cage and the rest of the zoo. That's a recursive solution to finding the lion. Probably not the best way to go about it. I don't think we have a lion in the Hilo Zoo. So some other bad jokes. I promised you that there would be some pretty bad dad jokes here. How do you put a giraffe in a refrigerator? Pretty simple. You open the refrigerator, put in the giraffe, and close the door. How do you put an elephant into the refrigerator? You could go with the same solution, but you actually have to open the refrigerator, take out the giraffe, and then put the elephant into the refrigerator. And so that tests your ability to link through the repercussions of your previous actions. So it turns out Lion King is hosting an animal conference. All the animals attend except one. Which one doesn't attend? Well, that's the elephant, and that's because the elephant is in the refrigerator. And finally, there's a river you have to cross in order to get to that meeting, but it's used by crocodiles, and you don't have a boat. How do you manage it? Well, you basically jump in the river and swim across. The crocodiles are attending the animal meeting, so they'll be going to see the Lion King as well. I told you bad dad jokes. So let's get into a real example of recursion. So, one example is the factorial function, which you may have seen in your calculus classes. So we start out and say 0 factorial is 1, and then for any number n, it's equal to n times n minus 1 factorial if n is greater than 0. So the first one, equation 15.1, is called the base case, and equation 15.2 here is called the general case. Factorial is probably not the best example in C++ because it overflows pretty darn quickly. And that's even if you're using a long unsigned int type. So you have to define a custom large number class. Works a little bit better in Python, but it's still going to drag down the processing speed. So take a look at an example with vertical numbers. And basically, a lot of times we write things horizontally on the screen. reading left to right? What if we wanted to write them top to bottom? Well, we can do that with recursion. And so we define a function. We write our declaration up at the top and say, hey, we want to write vertical. The precondition is n is greater than or equal to 0, and n gets written on the screen vertically with each digit on a separate line. So how do you go about doing this? Well, we're going to use recursion here. The simplest case is if n is less than 10. It's just a single digit. Then we write it to the screen, and hey, we're done. That's our base case. A typical case is we want to output all but the last digit vertically, and then write the last digit. So, that's kind of the line in the zoo joke. Step A is a smaller version of the original task, and step B is the simplest case. So we have our recursive case and we have our base case here. So let's take a look at some pseudocode for how to do this. So if n is less than 10, just use cout and n in line. Otherwise, it's 2 or more digit long. And basically what we do is we call the same function write vertical for n with the last digit removed, and then output the last digit of n. So the else condition here is the recursive subtask. And the successful definition of a recursive function needs to include a case that does not include a recursive call, along with one or more that does. So we have one that has a recursive call and one that does not. Well, how can we do this? Well, we need to recall some old friends from CS150, and probably half of 151, at least you probably discovered it so far, is, hey, remember all that stuff we learned in CS150? It comes back to roost. So a couple old friends from 150, n divided by 10 is the number n with the last digit removed. And n percent 10, that's the remainder modulus function, is the last digit of n. You're doing things in base 10, and you may have used these in a bank program or some other program in CS150. It's been a long time since I've taught CS150, but we used to use bank account programs and check digits, and that was a common task in 150. So our modified function is going to be write vertical. If n is less than 10, we still just go with the cout, and we put the n line in so they're on a separate line. That was one of our conditions. Otherwise, it's 2 or more digits long. We write vertical with the last digit removed. So, you take 123 divided by 10, you get 12. So, it writes vertical 1, 2, and then puts the 3. But we have to wait until write vertical returns in order to write the 3. So that's how it ends up writing vertically 1, 2, 3. So when write vertical happens, we suspend execution of the computation, begin executing write vertical 1, 2. When write vertical 1, 2 gets called, we strip off the last digit, and then we call write vertical 1, which is something we know how to do in our base case. That leaves the cout 2 and then the cout the 3. And so you can think of writing these on cards, and basically we have the write vertical 1, 2, 3 gets suspended write vertical 1, 2, and that gets suspended write vertical 1. And so that's called a activation frame. Or, we can think of recursion as a stack. We'll get into stacks as data structures a little bit later on in the class. But basically, we think of putting them as stacks and then popping them off the stack. So basically, it's a last in, first out. So the last one was write vertical 1. That goes out first. Then the 2 gets done, and then the 3. So if you don't have at least one case that does not depend, you need to have at least one case that doesn't depend on recursion. That's called the base case or the stopping case. And if you don't have that, basically you're going to get something called a stack overflow. You'll run out of memory, and then you'll have to download more memory, and that will be a problem. So, basically, you want to make sure you have at least one base case that does not depend on recursion. You also want the recursive case, obviously, but you need the one case that doesn't depend on recursion. And any task that can be accomplished using recursion can be accomplished in some other way. The non-recursive version is called the iterative version. And the trade-off is the iterative versions use less memory and they run more efficiently, but the recursive versions are often simpler to understand. If you think about something like the Fibonacci numbers. It's very easy to do recursively, a little bit more challenging to do iteratively, and Benet's formula is definitely hard to do direct. And we say recursive versions are simpler to understand, but I have had in 15 years of doing this, I've observed sometimes students do have trouble thinking recursively at first. So I put it as a trade-off. So let's look at another example, and this is a conversion to binary. If you're taking 266, or you've taken 266 or one of the discrete math classes, there's a process to convert decimal to binary, which basically relies on repeated division by 2 and taking the remainder and then reading top to bottom. This is a recursive version that actually accomplishes that. That's in the Malik textbook, and if you want, you can download and run that one. But basically, we keep calling decimal to binary while the quotient is not 0, and pushing things onto a stack, and that reads them in the reverse order, which is what we want. You can also have recursive functions for values. We're not just limited to void functions. The last two that I've talked about are void. Factorial isn't, but again, factorial is kind of a pathological thing in C++ and most programming languages. So to define a recursive function that returns a value, you need one or more cases in which value is returned, without any recursive calls, your base case, and one or more in which the value is computed in terms of calls to the same function, smaller arguments. The power function is an example of that. So 2 to the 4th is equal to 2 times 2 to the 3rd. 2 to the 3rd is equal to 2 times 2 to the 2nd. So you can see that we compute and get a smaller version each time. So for general recursion, check that your recursive part is correct, and check that it always results in a base case. You don't want infinite recursion. You don't want those Stack Overflows. Stack Overflow is a great website. Highly recommend it, for learning about programming, and really helpful. But you generally don't want any programs. You want a web browser. Each stopping case should return the correct value, and if all recursive calls return the correct value, then the final value returned by the function is correct. So those are the things you want to check. Another case study is binary search, and you may recall binary search from 150, 141, or even parts unknown. And basically use this to efficiently find a value in a sorted list. So imagine that we still had phone books, and I want to find Steve Smith in the phone book. Basically, I can start at the midpoint of that phone book and then determine whether Steve is in the left-hand side or the right-hand side of the phone book. If he's in the right-hand side, I take between the midpoint and the end, split in half, and then check again. So if the item's less than the midpoint, search the first half. If it's more than the midpoint, search the second half of the list. And if it's the midpoint, hey, you're done. So one of the cool things about binary search, I guess the first thing is it requires a sorted list, but one of the cool things about it is it's one of the fastest algorithms that we have out there that's not constant time. And basically each step in the process cuts the amount of work in half. And this is much more efficient than sequential search. Sequential search involves checking each item in the list to see if it's the one that you want. So, so for Steve Smith, we'd start with the first person in the phone book, see is that Steve? No, and then check the second person, third person, etc. That's not a very efficient algorithm, but sequential search works when the list is not ordered. So that's the positive for that. It's much better than linear. Sequential search is linear. It's O of n. O of log n is basically logarithmic, and so as the problem grows, the amount of work does not grow very much. It takes one extra step to find something in a list of 1,024 names versus 512 names. One of the other drawbacks of binary search is it's tremendously difficult to implement correctly. for programmers. And I think it took the computer science community something like 10 to 15 years to get a completely bug-free version of this working. So, hard problem, and that was back in the 50s and 60s. So as an initial design, we need to call by reference. Recall that pass by reference modifies the original. We need found to indicate, that we found it, and we need location to indicate where we found it. We also need to know what we're looking for. As the great director Ed Wood said, it's hard to find something if you don't know what you're looking for. And we need to know where we're looking for it, basically the array A and its size. So here's the first cut of the algorithm. We start out with found is equal to false. Calculate the midpoint as the approximate midpoint between 0 and the final index, and it can change depending on whether we have even or odd, determining that midpoint. If the thing that we're looking for is at the midpoint, we're done. Found is equal to true, and location is equal to midpoint. Otherwise, if it's less than the midpoint, then recursively search from the beginning of the list to the midpoint minus 1. Otherwise, search from the midpoint plus 1 all the way through to the final index. Any problems with this? Yeah, there's a couple of problems with this. We never say, never specify first and last value for our search space, so we need an additional parameter for the first, and size works as the last. Also, what if we don't find the target? Well, if first ends up being greater than last, then we haven't found it. And so basically you need to fix those two things. Those are a couple minor changes, and then you're done. And again, binary search is tricky to implement. There's a couple different versions. You're going to see several different versions in CS321 and look at the benefits and drawbacks of them. Don't confuse recursion with overloading. If you have two functions that have the same name and one includes a call to the other, that's not recursion. That's just, I guess theoretically interesting. Sometimes necessary, but most of the time not. And last but not least, I'll talk a little bit about how we think recursively. A lot of this comes from a book entitled Goedel Escher Bach, An Eternal Golden Braid by Douglas Hofstadter. And basically it looks at how the logician Goedel, the artist Escher, and the musician Bach all thought recursively and all had similar thought patterns. The book is from 1970s, but it's definitely worth a read for any serious computer scientist. It's one of the classics in the field. So, example of recursively, Fibonacci numbers. F of 1 is 1, F of 2 is 1, and the in Fibonacci number is the sum of the previous two. And that's the way we explain it to kids. That's easy. McCarthy 91 function is another example of a mathematical function, and the Takeuchi function down here, that one's just absolutely crazy. I don't think I've ever implemented that one in C++, but it's a pretty cool looking function. I've implemented the 91 function. It has surprising results. Another one is Hofstadter's function, and that's got some interesting mathematical properties that people look at in the realm of mathematics. It was something first proposed by Hofstadter in that book from the 1970s, and then married functions where one function f is defined in terms of m, but they're both defined recursively. So that's not just the overloading or the calls to another function. In theoretical physics, the interaction of an electron in a crystal with an electron in a homogeneous magnetic field is recursive, or so they tell me, and there are parts of relativistic quantum mechanics that are also recursive. I'm taking the physics department's word for this from many years ago, but I trust them. And language constructs. English is not necessarily as recursive as other languages. So, for example, German, wir haben alle unsere Verben an ins gesetzt. Basically, that translates to we have all of our verb on the end placed. So Germans tend to place the verbs on a stack at the end of the sentence. So the other one is Sie sollte Deutsch lernen, weil sie Sprache mag. So that basically has the you should learn German. You should German learn. So the verb goes on the end. We pop it off. And then weil is because, and sie, you, sprachen, to speak, may. So it doesn't sound the same in English, but the Germans use that recursive structure for verbs. And get into Japanese, which I do not know as well. Tanaka-san wa ocha onomimashita. Hopefully that was approximately correct. Basically, that's Tanaka. As for the tea, it is consumed, or he drank the tea. And again, that's a recursive structure. Bahasa Indonesia, I can do this one. Imas ada lelucon dengan burung gila sekali. So Imas has fun with bird, crazy very. So the modifier, the adverb for the adjective, goes on the end of a stack. And one of my students translated that one into into the Hawaiian language, and it also has that recursive structure. Recursive acronyms, basically it's where an acronym defines itself. GNU stands for GNU's Not Unix, and Zombie is an acronym and stands for Zombie Oriented Machine Bean Interface Engine. Computer scientists are some of the worst abusers of the English language. For example, architect is a noun, agile is an adjective, but agile is used as a noun. We want to get agile. Architect is used as a verb. So I'm not sure which one of those is worse. In music theory, we hear music recursively. We maintain a mental stack of keys, and each new modulation pushes a key onto the stack. We usually maintain a stack with two keys. One is the pseudotonic, the key the composer is pretending to be in, and then the true tonic key, which is the global key that it's actually in. So the other one is in literature, and this book came out in 1996, I believe, and it's entitled Infinite Jest. And he modeled it after the Sierpinski gasket, the triangle shape that we saw on the first slide. And so in the Sierpinski gasket, a triangle is infinitely subdivided into smaller triangles using the midpoint of its borders. So it's chaos on the surface, and its bones are its beauty. And there's a great time saver. The Decemberists made a 3-minute version of the 1079 page novel. And one of the cool things here is that it's very much a corporate oligarchy that runs the world, where this book takes place at a tennis academy. The years are named after different companies. So the year of the Yoshitsu 2007 Medic Resolution Cartridge View Motherboard, easy to install upgrade for information interlaced TP systems for home, office, or mobile. So there are different years. And it's actually a really cool book. The other thing is he writes sentences that are grammatically correct, even though they appear to be run-on sentences. So, this guy really had a huge command of the English language. And he actually had studied mathematics. So, book is definitely worth taking a look at. And I won't read all the excerpts. In art, these are Escher's fish. They're tessellations, and basically the object parts are copied onto the object itself. This one, we have the mapping and parts of the moths onto one another, and all of these moths are related and get more complex as you go more towards the bottom right-hand side. But there's, mappings between each individual moth. It starts out as white and then gets to this glorious moth. And lastly, in toys and games, Magic the Gathering certainly has recursive elements to it. I'm assuming Pokemon has recursive elements, and the Towers of Hanoi, which I'm certain you're familiar with, also has, that's a completely recursive game. So, basically move the all the rings from the start to the goal, and after that you're done. But you can't put a bigger one on top of a smaller one. So that makes it recursive, and I think it ends up being 2 to the n in terms of its computational complexity. So the original story was there were 64 golden discs, and the French mathematician who came up with the game basically said, when they moved all 64, the world would end, but you don't need to worry about that because it basically, depending on how long it took each one them to move each one, the lifespan of our planet would definitely be over by the time they had moved all of them. So you don't need to worry about monks moving gold discs over in Vietnam. Anyway, thanks so much for watching. Check in with you next time.